welcome to ESA's headquarters here in Paris. Today is a very important day in the life of Rosetta. I know I say this quite often, but today it's really decisive. We're going to announce the landing site for Rosetta's lander. And you see I'm framed by the proper experts here around the table. I will soon introduce them because they have been all key to the decision that was taken yesterday in a 2-day meeting in Toulouse at the French Space Agency's site there. And they represent all the important input that you need to do such a decision. That means from management point of view, from a science point of view, from the operational point of view. And you know, we had 5 sites left, and today we will go down to 1, the primary landing site and the backup. The program looks as follows. Fred Janssen, the Rosetta mission manager, will give us an overview how we came to where we are today. So he will give us, let's say, the bigger picture, why landing is so important. And then we have Stefan Ulamek. He is DLR's Viele Lander manager. He will tell us where we are going to land, and he will explain also to us what the descent means. And Holger Sirks, he's the PI from the Osiris camera. He will give us more details on this primary landing site. Then the scientific aspect will be covered by Jean-Pierre Bibring. He's from IAS Orsay. He's the lead lander scientist. And of course, this mission is about science. And we need to know why this site is really, really important for science. And even though now we have a landing site, we need also somebody to bring us down there. And therefore, we need to understand all the operational aspects. And Andrea Acomazzo, he's the Rosetta flight director from ESA, will give us some insight there. Fred Janssen then will let us know what are the decisive steps ahead of us, because landing will be in November. And then I think we have the full picture, and you might still have some answers, some questions, and of course we're happy to take them in the end. And with this, I would like to give the floor to Fred Janssen.
Okay, I'd like to give you a quick introduction of what we've been doing with Rosetta over the last basically 9 months, and what we have done in terms of getting to know the comet, because that has been an important element. On my first view graph, first we had the hibernation exit, which was a very daring enterprise. It was necessary because the spacecraft had to travel through a piece of space where there just wasn't enough power in case of trouble to get out. And that was a unique success that was never done, and it was actually an operational first for Rosetta. After that, we've spent a few months, February, March, with spacecraft configuration. We knew that certain changes on the spacecraft had to be made to tune the way we operate some of the systems, and that was done. And after that, we went to instrument recommissioning, which was also an important phase, because the instruments, of course, by that time were 10 years old, and we had to see that they all still worked, what had to be changed, etc. Then the science operations planning had started in parallel to these activities in the beginning of the year, and with science operations actually starting in full earnest in May. And in May, we also started a large series of maneuvers, some 10 in a row, very significant maneuvers, very big, very long. And these brought us alongside the comet. And what we did after that, effectively in an decreasing distance to the comet, was to learn to fly in the environment of a comet. This has multiple aspects. One of them is that the comet, we know, is an active body. There is gas flowing out, there is dust flowing out, there is gravity, not a lot, but enough to distort the spacecraft on its path. And we really have to learn how to optimally maneuver, because at the end of the day, when you're at a distance of 10 kilometers, you can't make big mistakes. You really have to be accurate. On my next view graph, After that, we did actually a large number of operational observations by the science instrument as input into the planning and the landing site selection process. The landing site selection process is a lengthy process. It runs about 2-3 months, and it has a large number of science observations and an immense effort by the PI teams of the orbiter to generate products in support of that process. And what you will see today is the output of this process, basically, and it's not finished yet. And you will hear later that we are continuing and what we will be doing further along. The science planning process for the next few months is a real challenging one. We have to deal with all the possible choices which can be made, which are a significant number. And I will give you more details at the end on what these decision points are, because there are still quite a few to come. At the end, actually, what we see today is the result of many, many processes, and which have come together to enable the landing site selection, which we can announce today, and in the forthcoming months, the lander delivery. And as we speak, Rosetta already is a very big success. We are flying at 55,000 kilometers an hour, 30 kilometers next to a comet. This is an absolute unique achievement, and lots of science has already come out of the mission. But today, we'd like to tell you about where to land. Thank you.
Thank you, Fred. And now we switch to another computer, manually, to get the landing site presented by Stefan Ulamek, the lander project manager from DLR.
Yeah. Good morning, everybody. I'm very pleased to be able to announce the landing site here today. As Fred has said, we've started our exercise last weekend with 5 pre-selected landing sites. And if you go to the next slide, you see an image you've probably already seen of the comet with 4 out of the 5 sites. In the next view graph would be the other 2. Which had the not 2 original names, A, B, C, I, and J. And these pre-selected sites were in the last couple of weeks investigated in much more detail in order to find really the best one from several respects for us to land. And if you come to the next slide, you see some of the criteria that have been used for this selection. So obviously there is certain characteristics of the site itself which are important if you want to operate the lander over there. It's the sun illumination. Is it on the summer hemisphere or on the winter hemisphere? How much sun can we expect also for the cameras? Then of course the topology. What's the local slopes? What's the terrain? Are there crevasses? Are there hills? What's the terrain on the landing site or on the landing area? How safe is it to land over there? And we also looked into boulder statistics. How much gravel is in this area, and we were using the Orbiter high-resolution OSIRIS camera to do these kind of statistics to again evaluate the risk of the various sites. Then, of course, there was the block of flight dynamics. This very particular shape of the comet doesn't make it easy to land. So we cannot land everywhere. For instance, in this neck area, it would be very difficult from flight dynamics. So we had to analyze also from a flight dynamics point of view which areas are good to land there and which areas are bad. For instance, the descent time varies quite a lot for some of these sites. This includes the required orbiter maneuvers, which are for the delivery important, and that's also not trivial to keep the whole mission safe. And then, of course, there are scientific criteria. We will have a presentation later on this. Of course, every spot on a comet is interesting and fascinating, but this was also something we considered. This also includes the compatibility with a radar instrument we have on board, Concert, which will do kind of 3D scans through the comet. So if you give me the next slide, you see, and you click it, some preparation of the information we had, which was actually done by CNES. And here you see again a three-dimensional model of the comet with color-coded illuminations. All the red areas are summer permanent illumination. Blue is permanently dark, like on the winter hemisphere. And here you see already our landing site we have chosen, and this is the landing site J. We've also chosen a backup site, which just comes into the picture right now, which is C, in case in the coming weeks we find out that something very unexpected happens with site J, either because there is boulders we do not see yet, or because there is some jet or something completely unexpected. And here you see the model of the comet, and the lander happens to sit exactly on our selected landing site right here on this model. If you go to the next slide, you see an image here of J, and just having a first look at it, you already see this is not an easy task. So this frame covers about our landing ellipsis, it covers about the area of our uncertainty of landing, and you see there is flat areas, but there is also rough terrain. There is some cliffs, there is some boulders, so we have to work a little bit with statistics. It's not a perfectly flat area as we probably would have hoped for a safe landing site. If you go to the next slide, you see how I'm too close to the micro. You see just an example of how we use this vast amount of data obtained from mainly the orbiter instruments in the last couple of weeks. This is a map showing slope statistics for the site J. Everything which is blue, everything which is light blue or green is relatively flat, but there is also these red areas where we have higher slopes, and those indeed may cause a danger for the lander at touchdown. We've done this kind of analysis for all the sites, and at the end J turned out to be the best one, but even here, as you see, the risk is high. If you go to the next slide, you see another image of our backup landing site. This has some disadvantages, also from a flight dynamics point of view. But for other respect, it would be an alternative, as I said, in case site J turned out to be bad for whatever reason. If you go to the next slide, and you click it for the animation. This is an animation where the lander is the point of reference. So everything else is moving. You see the whole situation as if you were on the lander or just on a camera behind the lander. And the good news for you is we have selected a scenario which only lasts 7 hours, so we just have to wait for 7 hours now until we land. So you see the comet is moving in respect to the lander. You see in an ellipse about our landing uncertainty, and you see how we descend to our landing site until we land there. And if you look very carefully, you will notice that not even in this animation we hit the target point exactly. Yeah? So there is quite some landing uncertainty. Okay, next slide. And this is now a high-resolution image taken by the OSIRIS camera. And this is also the point where I would like to hand over to Holger, the PI of the OSIRIS camera, to show you some even more detailed images.
Thank you, Stefan. So this is an image taken head-on the small lobe of the comet. You see the large lobe in the background. So all Rosetta remote sensing instruments and all Rosetta in situ instruments are supporting the landing site selection process and are taking a huge effort in getting their data provided in due time to support this process. So the red cross is where the landing ellipse centered. It's a bit beside this roundish spot right on top of the small lobe. So we did quite a lot of effort to characterize this surface, the morphology as we say, and found varied regions on this comet. So we're still debating whether it's a contact binary or a fragment of a larger comet that, from the Kuiper belt. So there is a lot of discussion ongoing, which might also lead from a scientific point of view into a selection criteria. So the little J you find on the top lobe here on the right side, you'll find it again on the next one. The surface is distinctly different in varied areas. So I think you all have seen activity already a little in the images published from Rosetta. So the pink area in the neck is very smooth and thought to be highly active already now. So we see jets sourced in this region. We have left and right some steep cliff regions where we also think we see first indication of activity. The Xion areas on the big lobe and on the small lobe, they are mantled. They are covered with grains, with material that could be redeposited on the surface and create a layer, a very smooth layer on top of the surface. Now we have a basal unit, this greenish stuff, on the big lobe on the right side here. And if you go with your eyes to these, to the top, to the head lobe again, you see the active, slightly active area where you can find the J. So let's have a closer view at J in this flicker movie. So the J is on the lower end, on the lower right, and this little movie gets you a feel for the three-dimensional structure, because this is most important, I think, to find out what is the topography, what is the surface looking like in this area. I brought this also up because on the upper left there are two pits, and pits we have seen in the active region showing early activity, and we see already here a first indication that these pits might become active. So from a scientific value, from a scientific point of view, the lander on J will be just 500-600 meters away from this active region, which gives us good access to cometary activity. If you zoom in into this area with just two different perspectives, you see these pits. They are fairly cylindrical, and we are discussing why they look like this. They have a pretty flat bottom of the pit, and show first activity. And so this is reachable from the in view from landing site J. That's an indication of activity seen so far from the very latest data. It comes out nicely here on the presentation. So the activity is not red, it's just enhanced. We see with the remote sensing instrument with Osiris and the telecamera, we see the dust reflections as a sign of activity. The other instruments, as Miro or Rosina, they see the gas directly. And so the comet is active already now, and we find it highly attractive to go to the small lobe, because we see a first sign on the left image already indicated there. And if you look a bit closer, we can source the spots of these two pits I have shown on the upper lobe, and they will become more active as we go closer to the sun. Coming back to the topography of the landing sites, so the terrain models, the shape model we created, we want to give you an impression on how steep the cliffs and the area is. So I want to blink you through a number of images, so you get a feel of so 1, 2, 3. So you get a feel also from the shadows how this area looks like. So the white cross is at the center of it, of the landing ellipse. And so by the shadows you get a feel of, it's not flat as Stefan said, it's It has quite some topography. And if you want to take your glasses, this is an anaglyph. You can even get a feel for the three-dimensional structures by using the anaglyph.
So that's red on the left.
Yeah, the red is on the left side, and so it comes better out on the screens than on the beamer. So it takes a little while to get a feel for the depth of the image, and so you get a good feel of how curved, how structured the area J is. And so the topography model created by our team is shown here. So this is a tile, part of the surface, the 1 by 1 kilometer square of this area, the J area. The landing ellipse centers in this tile. On the lower right, you see just a still image with the real image just put on top, co-registered on top of the topo model. So it ain't easy. So going back shortly, briefly into the backup side. The backup side has a little advantage of having the neck region basically in view accessible, but it has other issues there. So this is the C on the bigger lobe. So we have one on the smaller lobe, J on the small lobe, C on the big lobe, and again the little flicker between two images. So from one image to the other, you get a feel of So there is topography. It's not flat either. And with the glasses, you can also see a bit more how this comes out in 3 dimensions. So this comet has no real pad to land on. It has a topo everywhere. And so again, the tile of our DTM, it's highly structured. C is highly structured, and you also see a nice view on the lower right. So with this little animation, so looking from the lower lobe to the from the big lobe to the from below to the head lobe to the smaller lobe, I will hand over to Jean-Pierre.
My turn to say good morning to all of you and to emphasize how moving it is to be here today, knowing that in 2 months ahead of us we'll be landing, and 2 months is exactly the time since we met with the comet August 6th, so it's really almost in. And as it's been emphasized by Fred at the beginning, it's amazing how successful this mission is already. In 2 months, we have already acquired a huge amount of data that really we never got before, and actually this press event could be only dedicated to what we have learned for this comet already. Of course, the emphasis now is what we will learn in 2 months, and I'm very happy to be here on behalf of the entire science teams on the lander. As you know, probably the entire, we have, as you will see, 10 instruments on board, and the entire science is sort of led by 2 people, my colleague being Hermann Bernhard from MPS in Gothenburg now. So to give you an idea of the reason why we do all that, just 2 words on the framework, the big picture, as we say normally. I think to realize why we do all that, and the usual amount of people are really merging their skills and effort to make that happen, is really because, as I say here in a nutshell, we are really in the middle of a revolution of our thinking of how planets evolve. Why do we have such a huge diversity when you compare Earth to Mars, to Venus, to Jupiter, whatever? How that's feasible, although we know that essentially all the planets originate from a single solar nebula. What are the drivers of planetary evolution? It's even worse, if I can say so, when you compare the solar system to the other solar systems, stellar system that we see elsewhere. The diversity is really the qualification which now is really emphasized and exhibited by all the new discoveries we do here. And of course, that put the question that what drives the evolution? And I have just put out here 3 sentences just to tell you the sort of question that really have fundamentally revisited. What makes this diversity happen? Is the Earth unique in that sense? And if that's the case, to which scale? Is it within the solar system and then within the galaxy? And of course, that's even more true for what is harbored by the Earth, which is life. Is life a generic process in the universe or in the solar system? And if so, why? And so it looks like these questions, you know, very often for many missions you are really asking them, but it's really true to say that now we have a lot of possibility to approach this question in a truly scientific approach with representation based on observation that lead to new predictions and new observations to valid or confirm or opposite, demonstrate that the representation went false. And Rosetta is just there in between of that, because Rosetta is really in the core of that. It's not, of course, a mission that will answer all the questions, but will contribute in an absolutely unique way to answer part of these questions. In particular because comets, we know now, have been accreted and have preserved the process through which they accreted very early on, at the end of the collapse of the nebula, which finally accreted, in which accreted all the planets. And we know now the processes that build this sequence of accretion really drove the pathway to diversity here. So we need to know what are the processes. What are the building blocks in terms of the material themselves? What was the composition there? And as you will see, the composition is not only the elemental or molecular composition, but also the isotopic composition. What are the building blocks? What are the minerals? What were the gases? The water itself. We know that most of the water that we drink today come from the comet. But in a sense, okay, it's funny to say so, it's not the most important to me. The most important that we know that comets, which, although they are made of 80% of ice, should be the brightest place in the universe, and they are the darker. Comets are 3 times darker than the darker place on the moon. It's darker than this table. It's darker than the charcoal. And the question is why, although it's made of ice predominantly? And the answer is that it's essentially, it has trapped a lot of organic molecules, probably very refractory, very absorbing. We don't know the composition of which, because that's been discovered in '86 through the comet Halley flybys. We know that this material exists, but we don't know what the composition is precisely. And what happened at that time is that we thought that these molecules might be fundamental, because then coming with the water in the planetary oceans and probably in the Earth's oceans very early on, it might have contributed crucially to the emergence and then adaptation, evolution of life. So we desperately need to know the composition, because in that composition we might have an idea what really is specific to what will lead to life. And of course the next question will be, is that specific to the way our solar system evolved, or is it a truly generic process in the universe, and then life would be spread over everywhere? So the question on whether or not we are alone in the universe is really directly connected to what we are looking for here. So Rosetta specific is that for the first time, as we already started again, we will closely characterize that material. We have not yet been so close with all the 20 instruments on board, 10 on the orbiter, 10 on the lander, that will in a coupled way leave us the possibility to understand what the comet looks like in terms of the physical properties, what it is made of, the composition, internal structure, the activity themselves, what the energy source of that, what is the pattern, what the fate of this. And Olga just showed you an image which is originated from him, really, from the team, which is absolutely spectacular. When you see by the stretching of these images has been done by these people a few weeks ago, or a few days ago even, that essentially the activity comes from topography things. Essentially, this comet might have been pretty rounded some while ago, but of course, as soon as you have the merging of the possibility for that gassing to go, it increased the pattern, and now we have almost 2 blocks that might divide actually in the future. The dream would have been that that happened just the day after we landed, so we'll be the first to see the disruption of a comet, but probably it will be the next time. So Rosetta is very specific and of particular for the composition. We need to know the composition, and as you will see, we will try to have composition measured both elemental, what are the elements there, as a topic for at least the light element, and if I have time, I will tell you why it's so important, and molecular. What are the molecules at each stage, ICs and organics? So, just 2 words to remind you that over the past 2 months, and actually since July 15, when we got the first images, we were very scared at the beginning. At the beginning, it was so scary to see this comet as it was. It was really unexpected, unpredicted. No one really in the model thought that we would face such a comet. And when we saw it rotating, the first view was, we won't be able to reach any place there. It was really scary. But then, as soon as we get closer with splendid images from Osiris, from the NAVCAM, and then many other measurements that were performed splendidly from the other people, suddenly it happened that we might really have reachable areas. And then I should really acknowledge the splendid work done by Flight Dynamics, both at ASOC and at CNES in Toulouse, to demonstrate that although this body was unexpectedly exciting but very scarcely, there should be reachable areas. So it was fundamental, because then we discovered that we could land and really contribute to what we wanted to, contribute to understanding this comet. That's an area, the area in which we are, I plotted in the image that I'm sorry I love, because that's an image taken a few days ago from the lander itself. On the lander we have camera that will be operational, of course, in 2 months from now, and that's the famous auto-portrait images when we see at the first glance the solar panels and the comet on the back, and this is where we land if you see the arrow in red, and that the enlargement here, and you know here where we are now, thanks to this NAVCAM camera, and that the enlargement from Osiris here. So really we have gone this spectacular zooming here, enabling to know where we might go here. And I will tell you now why we chose that and what the sort of science we can do here. And this is a list, I will not go through all of them, of course, of all the measurements that we will try to process and to proceed and perform as we are there. And essentially it goes first from capability to monitor the global properties at global scale. What is the internal structure? Is that body stratified, homogeneous? Is that a nucleus within the nucleus? What is the material inside? Are there any processes that already try to make some sort of differentiation, although it will be spectacular because we don't expect that? We have for the first time the means to do so through an instrument that will both operate on the lander and on the orbiter during a complete revolution of the nucleus as seen from the orbiter. We'll also, for the first time, be able to characterize the structure from the magnetic field. We do not expect, although it might be, that the nucleus is magnetized. It would be a big discovery because it has also a lot of outcome. We don't know yet, but we have the way to measure that. And also we'll measure the modification by the nucleus of the interplanetary magnetic field, which is driven by the sun itself, by the solar wind. Then we'll go to regional scale. During the descent, we'll zoom progressively the area in which we land, and we have a lot of means to measure the regional scale. When we land, we'll make the 300 degrees, 360 degrees panorama, of course. We'll also measure the gas pressure, which is really a big unknown there, the distribution of the gas also in 3D. So that will be done immediately after landing. And, of course, we'll have the capability when we land to measure, I would say, essentially most, if not all, the properties of the surface in which we will land. The mechanical properties, the physical properties, electrical properties, what the dielectric constant, for example, that's also key to understand the evolution of this body. What are the thermal properties? And that's important in particular because either are energy sources, you will have a gradient of temperature from the surface down to a few tenths of centimeters. We have the means to measure that because we have sensors that will be locked within the subsurface and we'll see the gradient of temperature, and that will be a direct indication of the thermal behavior and the energy behavior of this nucleus. But then, of course, we have a huge band of instruments which are devoted to analyze the composition down to a microscopic scale. And that's fundamental because, again, we never were able to measure the composition of the nucleus, of the cometary nucleus, really there prior to any outgassing or prior to any even transportation down to the ground, because you know that we might have on the ground some cometary samples through micrometeorites, but they have been processed by a huge number of processes to be extracted first, then in interplanetary medium, and then back to the Earth. For the first time, we'll be there and measure the composition prior to any modification by the sun or ejection. How shall we do that? we have a drill made by the Italian Space Agency under their responsibility in Milano, and we'll get samples up to 20, 30 centimeters below the surface. Why that? Essentially because we want to ensure that the material we'll analyze have not been modified even very slightly by the last transport of the comet in the solar system within the past 6 years. So we'll really get pristine material, as pristine as possible. And then these samples will be delivered to 3 instruments in sequentially, essentially, as we would do here. You take a sample and sequentially you transport it to different instruments, less and less, more and more distractively. And it's these instruments that will tell us the composition from the elemental to the molecular composition. And for the elemental composition, we have an add-on instrument that will work independently of these drill samples, which is an APX built in Germany, that will essentially, as we do on Mars, for example, just be dropped on the surface, analyze the X-rays and the alpha pattern of the samples within a few millimeters square. And finally, we have some microscope, both in the visible and the infrared. So all this suite of instruments, coupled to not identical but similar instruments on the orbiter, will give you from the microscopic scale to micrometer in size down to the, I would say, macroscopic scale, as in from the orbiter, a complete view of what these comets, how these comets behave, what the composition, either a modification of the composition from the material below the surface up to the time it's in the coma itself. That's not known for the moment. That will be fundamental to conduct in the future analysis of what we see outside and then try to translate that to what was in the nucleus itself. So this is essentially the instruments how they are labeled here. I'm not going through them. If you're interested, of course, I can emphasize that in a discussion afterwards. And that will essentially end my very little presentation to say that the reason why we chose J is because J essentially meets all the criteria we wanted to be able to fulfill the entire science sequence. In other words, in J we know that all the instruments, including CONSERT, including the microscope, including APX, all of them will be able to operate at least once to their full capability, to have one full rotation for CONSERT, to have at least one sample drilled and transported to all of the instruments that are needed for their instrument to be performed at least once during first, what we call the first sequence, which is what will be operational just after we land during the next 2 days typically, so typically November 12 and 13. But then, although immediately, we will run to what we call the long-term sequence, the LTS, because the illumination should be sufficient after the proper orientation, optimization of the orientation of the lander, to conduct immediately what we call the long-term science, with only the rechargeable battery on, and that should be able to cover the entire measurements to investigate the activity itself. So J is the site within the 5 that ensure the best that the entire goals we have would be met. So in principle, we are ready now to go to achieve a successful mission coupling the orbiter and the lander science. Thank you.
Thank you very much, Jean-Pierre. I think we now understand what it is, an icy treasure trove. Having said this, we have a landing site. We have enough reason scientifically to do this, but we need somebody to get us down there, and therefore we need flight dynamics, we need operations, and Andrea Comazzo is the flight director for Rosetta, and he's going to explain to us now what are the next steps.
Thanks, Marcus. After having heard all these fascinating wishes and hopes from the scientists, and having seen the pictures also from Osiris, you can imagine how privileged we feel to be the ones to have to land this object on the comet. But at the same time, you can understand the level of responsibility that sits on or lands onto our shoulders. So this will be definitely a challenge. It's not negligible what we have in front of us. I would say we've spent years with the colleagues of the lander team, mainly the colleagues from CNES and DLR, to work out strategies, to redefine them, to trade them off, to negotiate them, to fit all the constraints and the objectives we have for this operation phase. And now we have to implement it for real. Time has come to make it happen. What we have to do from now onwards is, in my opinion, is based on 4 main pillars. We have to find first a viable solution. We have to merge it with ongoing operations. We are still flying around the comet at 30 kilometers from this rough object. It's not negligible the efforts we have to put in achieving this. We have to validate what we have found and train for it. And in ultimate instance, we have to conduct this kind of operations, which are unique, and nobody has ever done anything like this. So if we can go to next slide, Marcus, please. This is what I meant, is we have to find a viable solution. What you see here on the screen, on the left side, is what we call space of solutions. These are potential trajectories of the spacecraft in yellow, and then the lander alone in light blue, going down to the comet. Unfortunately, we cannot fly the spacecraft on the right side of the blue triangle. We have to fly on the left side. It's a bit difficult to see, but there are a couple of lines on the left side of this triangle, and this is the accessible space for the spacecraft to deliver the lander. These are preliminary analyses we have done in the past weeks for landing. Now we have to implement the operational one. Once we have found a trajectory that can lead us or lead the lander down to the comet, we have to verify that this is compatible with the surface we have in front of us. We have already seen in the images from Olga how rough this surface is, how variable it is. There's no better landing place on the surface of this comet. This is what we have to cope with. Unfortunately, our error ellipse is relatively large, but we are flying around an active object, a very irregular object, and this is what we have to cope with. So what we are trying to do as well in the coming weeks is to maximize the maneuvers and the separation condition such that they maximize the chances of landing successfully on this type of surface. If we go to the next slide, Marcus, please, we see what we are doing right now. Right now, we are flying a very complex set of orbits around the comet. You might have heard it in past weeks. We are currently on circular orbit at 30 kilometers from the comet. We still have two major points, decision points, before even we get to the lander on what to do with the spacecraft and the orbits around. In the course of this week, we will decide whether we go down to 20 kilometers orbit. We are still evaluating the performance, the navigation performance of the spacecraft around the comet, and we will evaluate in the course of this week whether to go down to 20 kilometers. Later in October, we will also decide whether to go down to 10 kilometers orbit. We are still uncertain whether all this is feasible. And all this has to be merged with what is coming up for the lander. What is displayed here in red is the potential trajectory of the spacecraft we'll have after we have finished the 10 kilometers orbit successfully in October to go to the landing site, to deliver the lander, and to guarantee operations afterwards. So if we go to the next slide, the next pillar is to validate all this and train for it. The teams are very familiar with operating the spacecraft, but there's still much more to do. As I said earlier, the type of operations we are going to do, the timeline we are going to have are unique, extremely critical, extremely demanding in terms of effort. We're doing all what we can, all what we are in a position to do to prepare at best for this operation. What you see on the left side of the screen, these are simulated images of the comet. We have a 3D shape model of the comet. You can see some printouts here. We are already simulating images that we will acquire the day of landing, and we are trying to maximize the chances of have a very accurate navigation of the spacecraft. So we are selecting already now the timing at which we will take the images such that we maximize the chances of exploiting all the features that are in there to have an accurate navigation of the spacecraft. In parallel, we will run what we call a simulation campaign. This will involve several teams going through the timeline, exercising the timeline, and having the whole team familiar with it and ready with it. We have very time-critical operations we see later on. What is on the right side, you see real images of the comet superimposed with our models. They can display where we should expect shadows, where we see landmarks, where we should expect the edges of the comet. So we are preparing all these kind of tools as well to maximize the chances of a very accurate navigation of the spacecraft to deliver the lander. And if we go to the next slide, thanks, you see a sketch of the timeline. You see on the left side the trajectory, the preliminary trajectory we have designed for this landing site. The spacecraft is coming from is flying on the white line from the right to the left. So we are in orbit around the comet. We interrupt this orbit. We fly closer to the comet. We go downwards. We release the lander, and the lander is going down on the yellow-green line, as Stefan displayed earlier in his movie. Immediately after, we have to do a maneuver to guarantee visibility of the lander throughout the descent and up to landing. This is fundamental. And on the right side, you see all the timing of this. 11 hours before the separation, we acquired the last images and we performed the last orbit determination of the spacecraft to navigate very accurately to the release point. At -7 hours, we uplink the commands for separation, but we have to decide together with the lander control center in Cologne whether we are going to separate or not, whether everything is ready or not. At -2 hours, we do this maneuver that moves the spacecraft away from an orbital status and flies in front of the comet, so to say, to deliver the lander. And 2 hours later, the lander is separated. The descent time we are considering for this specific landing site was already mentioned by Stefan, is in the order of 7 hours. In these 7 hours, we intend to observe the lander as long as possible, but we cannot do it immediately. The first thing we have to do is this maneuver that guarantees this visibility. This is done 30 minutes after separation. And an hour after separation, we should be in a position to point the spacecraft to the lander, acquire images, and get the radio frequency link. And then the spacecraft goes farther away from the comet, and we'll have to continuously maneuver actively the spacecraft for a few days in order to be able to communicate with the lander. So this is the most critical operation ever we've done for sure in the control center in ISOC, and we're preparing for it. So if we go to the next slide, that concludes my talk here. I've reported what in my opinion is absolutely needed to have a successful landing. We need both Rosetta and Philae working in synchronization, super synchronized. We've been working, we are still working with the colleagues in Cologne mainly to make this happen. We need very accurate navigation of Rosetta. This is the most challenging part. We need a radio frequency link to be able to communicate with Philae. We need to get data back from Philae. We need to see whether Philae has landed or not. We don't need the radio frequency link to steer Philae. Philae is falling onto the comet, but we need this link to have data back. Only with this data, we can see whether we were successful or not. And then we have the touchdown. This is the only part for which we cannot do very much. The comet has to play with, all the other variables has to play with, but on the touchdown, you have seen the surface. There's no better landing place on this surface, on this comet, but this is what we have to live with, and it's the only way we can achieve it. So thanks for your attention.
Thank you, Andrea. So there are still 2 months ahead of us. Busy, critical. And I would like to give the final word to Fred Jansen, the mission manager, to wrap up, but also to give us an idea what is going to happen in these 2 months.
Yes, the next steps on the way to landing. I'll try to give you an integrated picture of what we're going to do. And actually, the subtitle correctly is Meeting the Challenge, because we have to put everything together now. Because not only, on the next view graph, you'll see we are not only, in inverted commas, trying to land, all the other operations in the meantime have to continue, and we also continue to map the landing sites in increasing detail. So all the activities we now do are on the primary landing site. There is a backup, but we go forward with the primary landing site. Detailed analysis of the lander trajectory, as Andrea explained, and all the related operational activities will be going on, really making sure that operationally we can get there. However, the complexity is not only in getting the right orbit to get to the comet. We also have to make sure that in planning we can live with these points of decision. Do we go from 30 to 20 and from 20 to 10? For each case, we have to have science planning ready. Now, if you realize that the science planning cycle is typically of the order of 2 months, then we have to have all these ready ahead of time. So at the moment, we're performing something on the planning side, also what we've never done before, namely we're planning 4 plans in parallel. And all the PI teams are generating all the commands and all the pointings for all these plans in parallel, which is an immense challenge. By September 26th, we should be in a position to confirm the lander delivery date. On the 12th of October, there will be a meeting of the lander consortium and ESA where we will confirm the go, no-go for the primary landing site. What does that mean? At that point in time, we will use all the available additional observations from OSIRIS and the other instruments, and the analysis done, looking at boulder maps, etc., to see, is Site J not hiding something which we'd rather know before we push out the lander? Then on the next view graph, on the 14th of October, the decision will be confirmed in a review at ESA director level with the Lander Consortium participating. And it will not only look at about what is the result on the landing site selection, is it safe, but also all the operations that Andrea alluded to. Has the training been done? Are we ready? Are there things we've overlooked? And that will be the real point where we say we're going to land on the primary landing site. Should it not be possible to go to the primary landing site, we will basically have to repeat all the analysis that will be done between now and then. We might be able to skip certain steps, but there is a potential delay in landing then of up to 28 days. If we're lucky, it could be a few days. Worst case, it's 28 days. But the point is, at that point in time when we say, well, the primary landing site cannot be reached, we'll have to establish an entirely new timeline to work exactly the same trajectory, but skipping a number of steps we've already done. On the next view graph. Of course, you will have picked up the word risk. Now, what about risks? Originally, we were all thinking that we would get to some kind of rounded, potato-shaped like comet with evidently rough and structured terrain. Based on that, the estimation at the time of the probability of successful landing was somewhere between 70 and 75%. You will realize that the complicated double structure of the comet really complicates and has an impact on the overall risks related to landing. None of the landing sites actually meet all the engineering criteria to 100%. You've seen the DTN map with these red colored ridges in the middle. So there are risks there as well. So lander delivery has to happen for the mission to be able to continue. So we know there is not much time, and full risk analysis cannot be repeated at this point in time. What we're focusing on is to actually optimize all our processes, select the best possible landing site, which we've announced today, and then we go into operations and do our very best and optimize our processes to make sure we have the best possible strategy to reach the landing site. On the final view graph, there are two things I'd like to say about science, which has not been mentioned extensively, at least orbiter science today. The lander science observations, besides having their own merit, will allow to place many of the orbiter observations into perspective. Bear in mind, however, of course, that besides what Jean-Pierre already mentioned, all the immense science we have already achieved and the success we have achieved with Rosetta, there still is 13 more months to come when the mission escorts the comet all the way through perihelion, the closest approach to the Sun. The comet will get to its maximum activity levels, and then we will escort it back out again. So that was my presentation. Thank you.
Thank you very much, gentlemen. And somebody is already anticipating the next part of the program, which is very fine with me. Of course, we are coming now to your questions. The only request I have, please state your name, the media you're working for, and if you're lucky and you sit in front of a microphone, then please use it by pressing the button. So the gentleman over there on my left side.
Thank you, Richard Ingham from the French news agency Agence France Presse. I have a question about the surface granulometry of the comet. To my untutored eye, it seems to me that you could have areas in which you have slipping and sliding areas of kind of gravelly substance. Is this true? Has it been taken into account? My other question, which is connected to that, is about any risk of outgassing near the landing site when you're trying to put the lander down.
Let me take this, at least for the first part. So there is, in our view, the surface is dry. So it's dry like hell, so there is no way to slip on the surface. Even the mantled region will provide sufficient strength to hold the lander on the surface. So we will see different strength regimes on the surface, but to the best of our knowledge today, all compliant with the landing event.
Maybe I can add just one or two words. Yes, we have some information of what the material might be at the surface, and I should have mentioned that maybe before. First of all, we know that there is no ice visible, and there is not a droplet of something that would be immediately seen in infrared, because infrared is very sensitive to water in whatever format it is, down to the resolution we have with Virtis, which is a brilliant instrument, which went down to 10 meters, so it could be, of course, much smaller than that, but at 10 meters, we do not see any droplet of ice anywhere. But the same instruments, together with Miro, actually, and other instruments, give us something very important, which is the way the temperature evolves with time. When your local time evolves, when you go from sunlit to dark, you see how the material behaves, and that tells you what we call the thermal inertia, and that's directly connected to the sort of material we have in the granulometry. And the thermal inertia is very, very low, which means that essentially where we will land, it's a material which is very fine-grained, and probably it's small grains. We don't know the size of the grain, but probably very small grains, to probably centimeters at least, and probably meters in some places. And importantly, I should have mentioned that we know that the composition is essentially carbon-rich, and that's why we are so happy with that side, that this side, as others actually, will immediately tell us the composition in terms of the organics, because they are immediately there in form of small grains. Remember that most of the organics are not small molecules that will evaporate immediately, that can be really rather like grains, organic grains, and that might constitute the mantle in which we will land. So sliding on that is probably very unlikely.
Thank you, Jean-Pierre. The hand goes up again on the left side. Do we have a microphone, a handheld? It's coming. Just a second. Thank you.
Le micro arrive.
Jean-Pierre Martin, Société Astronomique de France. But I will limit to two. One, okay, well, I will try two. But I thought at the beginning we were talking about a landing sequence of about 2 hours. Now it's 7 hours. Do we change the altitude for the separation? And if you allow me a second question, very short, what if Rosetta is not in view of Philae? Do we store the information on Philae? Sorry, thank you.
I can take this. So I start with one, and indeed some years ago we were anticipating shorter descent times. Now for each of the landing zones, actually we have studied 2 scenarios how to land, and it has to do with the mechanism which separates the lander from the orbiter, which has a nominal mechanism which can be adjusted to the delta V, so the velocity the lander is pushed back in orbit to fall down. And there is also a redundant system which is based on a spring. And this spring device has been designed still for the Virtanen case, a much smaller comet. So this velocity is in the range of 18 centimeters per second. And whenever we try to have a scenario where the spring mechanism is a real redundancy to the nominal mechanism, we have to separate the lander from a higher altitude, and we end up with a longer descent time. That's why these 7 hours in case of landing site J, which is kind of a drawback as compared to the maximum push-off device, but it increases the robustness of the separation itself. Yeah? Your second question was? Yes. The lander itself has a central computer, including a mass memory, so we can store the data on board of the lander until there is visibility again with the orbiter to dump them. Obviously, we cannot only have a limited amount of data, so one of the criteria for the landing site selection was that the geometry, as compared to the orbit of the orbiter, allows regular visibilities to get the data to the orbiter and then back to Earth.
Thank you, Stefan. On the right side there was a lady, and then we take the gentleman. Yes, thank you.
Paola Antolini, International Press Association, publishing for Il Sole 24 Ore Milan. My question is for Jean-Pierre Bibring. So first of all, I want to thank everybody. It's really a pleasure to be in touch with the scientific community and also the ESA community since more than 10 years now. So if I understood well, because there was a question that remained inside since Darmstadt, where we had not the floor. Coming back to the concept of diversity that Jean-Pierre evocated, if we understood well, this is an unusual comet, also in terms of temperature. It's a hot comet, no ice, and also on the human factor, on the human touch. How many working human hours we have on this comet, that sometimes we forget how many scientists and technicians are working on it. The civil society participates since the beginning, also for the waking up Rosetta, and for sure now with the landing. But how and what the civil society can get from the data, and what will be the longevity of this mission, that it will cost only like 5 days of war in Iraq. So I think that for us, we are very glad about all these results. Thank you. Just take opportunity to remind also this friend, Angioletta Corradini. She was the principal investigator of the eyes of Rosetta. So what this Virtis instrument, optic eyes and red eyes, are able to see and to send us. Thank you, Jean-Pierre.
Okay, there are 52 or 53 questions in your question, so I might not answer all of them. The Iraqi one I might just discuss later on. The diversity first. Yes, diversity of the solar system is something that we see now after 4.5 billion years of evolution. What was the initial state of diversity, we don't know. Is that comet representative or not on what we consider the comets are? We don't know the answer, of course. That's the first time we're only with a comet. There is a lot of arguments saying, well, most of the material created after a given, let's say, 1 or 2 million years probably look the same, in the sense that they essentially assembled the material that we had available at that time. We just didn't know what it looked like. Rosetta tells us what it looks like. But the diversity I referred to is the diversity after a much longer period of evolution, not that one. The question of the temperature that you quote, which is important actually, you refer to a measurement by Virtis, the great instrument that Angioletta was leading for such a long time. This instrument has discovered that the temperature is higher than expected, but it's not true. The high temperature is directly connected to the fact that there is no ice at the very top surface. This material which covers, what you call the mantle, this material that covers is essentially organic material, essentially very dark, very black. The darker you are, the more absorbing you are, and so the hotter you are. And so it's not unusual and it's not unexpected. It just demonstrates or is coupled to the fact that essentially no ice is present in large entities, at least at the surface. But again, when we say very hot, be careful. It's hotter than if it was ice, but it's still very low temperature. It's typically -80, -100 degrees C during daytime. That again, it's at the very top surface. Another instrument mirror that measured the temperature a little deeper showed that you might have a huge gradient of temperature, and you reach the sublimation temperature of ice a few meters, probably even maybe less than that below the surface. I think that's sufficient for answering the question, right?
Yes, the diversity also in this slow approach and delicate approach. We do not explode a comet like Deep Impact, we land gently. How many scientists work on it, and an average of the human contribution for this comet approach and rendezvous? Thank you.
Difficult to say because a lot of people contribute to a space mission, the one who work in, space activity just essentially merge a lot of different contributions. To go to the minimum things, we have 20 instruments on board, essentially, coupling all of them. How many people work on an instrument typically? You would say anything between, it's decades. It's typically anything between 10 to 100, depending on the instrument. So on an average, if you put 20, 30 people, scientists, plus all the engineers, you have to multiply by 2. Multiply by 40, you have the number of people involved directly to the instruments. But to the manufacturing of the instruments, you much more than that, because the institutions are there. And then on top of that, you have all what make this mission available. The instruments are just one part, the final part, but then you need to have a vehicle, and then you need to have a launcher, plus all what that means. So actually a mission like that merge the effort and skills and talent and excellence of hundreds of people, and probably several thousands of people. Now, if you want to trade off with the outcome, again, to me, the outcome is enormous, because I started with that. The revolution we are in by space exploration beyond the scope of Rosetta, but essentially through what in particular ESA has done, has tremendously changed our view of what the Earth looks like. And that's essentially irrigate a lot of activity fields of human society is, in general, much beyond the scope of the mere scientific community. So I think if you want to trade off really what we do in space exploration to the outcome of that, you've got to realize that really the view we have of, in particular, the question whether or not Earth is unique, it's a global thing we've got to deal with. There is no way to do elsewhere what we have on Earth and that sort of thing. That goes much farther beyond the scope of a mere result that we get with Rosetta. It's just contribute to that.
Thank you, Jean-Pierre. Yes, please go ahead.
Olivier Sangui, Cité de l'Espace Toulouse, enjoyspace.com. My question is, I think, more for Mr. Akomazzo. Given the flight dynamic, and only the flight dynamic, do you have dates where you know it is impossible to land on site G, and preferred dates? What are your constraints for the dates of landing?
I assume you refer to landing site J, because we had this discussion in the past days between G and J. Technically, there's no real constraints. Any date is okay. The comet is rotating with a period of roughly 12 hours, so technically we have 2 opportunities per day. The difficulty is that we have to phase, as I said earlier on, the orbit after what we have already planned till the end of October, which is this 20 and 10 kilometer circular orbit. They are there, they are secure for scientific objectives to be achieved before landing, nothing to do, or partially related also to the landing, and only afterwards we start phasing the orbit of the spacecraft to meet the landing site. So this is some technical, let's say, timing to be there, but there's nothing preventing to land on one day or another day.
Thank you, Andrea. Any other questions? Yes, please go ahead.
Right, yes. Jonathan Amos, BBC. I wanted to ask about the possibilities for a dress rehearsal, but first just to push this if I can, Fred and Stefano, 70% if it was a rounded object. I mean, what's your best estimate now that we've got this duck shape and you've got to get down on it when you wake in the middle of the night in a deep sweat? What do you think? What are the chances? Are they better than 50-50?
Well, I don't sweat at night, not at all. This is such an easy mission. Well, as I said before, we only have the original estimates. We are not going back to nickel and dime on all the potential uncertainties. It's just, it would take a lot of time, and it would only give us an under number. I I have no real number in mind of what it is today. And we will do, as I said, we will do our very best to optimize all our processes to get as close as possible to the original number. And that's all I can tell you.
And the issue of a dress rehearsal, Andrea?
Yeah, maybe I take this one. We definitely consider this option. Unfortunately, there are some drawbacks because of the trajectories we have to fly around the comet. In order to be able to deliver the lander successfully, we have to fly relatively fast in front of the comet. And this brings the spacecraft again on hyperbolic orbit, so we are not bound anymore to the gravity of the comet, and it takes quite some time to get back. So if we were to do a dress rehearsal, first we will engage a lot of time, and this is very precious for the other instruments and for the lander itself. We would do this operation at a later stage with higher chances of having a comet that is more active. The second thing is what dress rehearsal can bring to us is knowledge about the accuracy on the navigation of the spacecraft. But if we do something a day, it doesn't mean that 3 weeks later we will have the same conditions from the coma of the comet, the activity level. So we traded it off, and we decided in the end not to implement. Of course, on ground, with the tools we have on ground, we have simulated all this phase. We had Phil talking to the spacecraft models that we have on ground, and this is all validated on ground.
Thank you, Andrea. Thank you, friend. Any other question from the audience? Yes, the gentleman in the blue shirt.
Hi, I'm Cyril Van Abel from Le Figaro in Paris. On a flight dynamics point of view, you said you were doing some modeling of the shape of the comet and trying to compare with actual observations with the high-resolution cameras. Could you tell us what results you have on the precision of your trajectory?
Yep, now it's released. There are two issues in flying a spacecraft like this. One is the capability to reconstruct the past. So it was what we call orbit reconstruction, and to know where we were. In this, we are relatively precise. We go down to a few tens of meters in being able to reconstruct where the spacecraft was, for example, when it shot an image or so on. A totally different business is to predict where we will be, so the orbit predictability. This is strictly linked to the models we have of the comet, the gravity model, the shape model, the knowledge of the landmarks we use as reference point, but mainly the knowledge of the aerodynamic environment around the comet. The comet is coming out from the comet. Olga's picture already showed that there is gas coming out. This is impinging on the surfaces of the spacecraft and is blowing the spacecraft away from its trajectory. So to predict this is much more difficult. Currently, I don't deny that we see these effects, but we are not in a position to discriminate them completely from the gravitational forces. So in predicting the orbit, we are still less accurate than in reconstructing, and we will not improve because the comet activity will further improve over the year. And this is the big difficulty of Rosetta, is to be able to predict. So and this is also linked to the performance of the spacecraft itself. To fly this type of orbits we are flying, we continuously maneuver the spacecraft, and the maneuvers done with the thrusters, with the propellant, they're not perfect. There is a certain inaccuracy in executing them. This also introduces a source of error that might sound very small, but with the very small orbital velocity we have around the comet, this can expand to a few hundred meters of couple of kilometers. And when we are flying at 30 kilometers distance or 20, then can be significant. So our capability to predict the orbit is definitely lower than the capability to reconstruct the orbit, and is in the order of a kilometer or so.
Many thanks, Andrea. Somebody else? Again? Okay.
Can we just talk about some of the structures, the features that we see on the surface? You get these areas that look kind of fluffy, and then you get these very tall, thin rims. Sometimes you get these protrusions with knobs on the top. What are the discussions in the team about how these features are formed?
Well, I mean, this is so we are landing very early in this mission, and this is also on our side, on the science side, the beginning of the discussion of trying to understand this comet. So we are not there yet giving real clues or real answers to this question. So one of the discussions we are having is the smooth terrain. I think I alluded to this already. So this might be dust that did not reach escape velocity and just fall back material that within this very low gravity environment just build up a highly porous layer of several meters or even several tens of meters thickness. And we have first indications of this material also flowing downhill down the gravity field. The compact material is, I would say, more of a challenge. And we didn't expect this rocky type material in a low density, low gravity field environment. So I remember the density is about 0.4 gram per cube centimeter. So it's a very low density material. So you can't have boulders or rocks or real cliffs up there. So one of the discussions we are having is shock compressed material. This guy has seen impacts as any other body in the solar system, and so with a fluffy, low density, highly porous material, you have an impact, you create a shock wave, shock compact material that is then depleted by volatiles and will just stay there forever. And so that would be one possibility. And then so this would get thermal, would also be exposed to thermal stresses. And we know from thermal stresses, we have seen some 4 Kelvin per minute or so is a gradient that is imaginable there. This will break the shock compressed material apart. But that's only a hypothesis. So we are going to work on this because somehow it has to be consistent with the 0.4 gram per cube centimeter density.
And you can grow pinnacles like that, can you? These tall, thin. You see craters that have these very thin rims.
Yeah,
and the pinnacles.
I wouldn't say you can grow pinnacles. The pinnacles are the leftovers. So all the rest is just sublimed away, carried away. So the dust is carried away. All the fluffy material is carried away with the gas field. And what is standing, what is residing there is the leftovers. The pinnacles are just, they were just not carried away. So are standing out of an evolving surface and just didn't make it away.
Well, I wanted to say maybe one word, not necessarily on that question, but the previous one, on the rescue hulls, or this question of navigation risk and that sort of thing, as seen from our scientific perspective maybe. Maybe what is not really well understood is the fact that for the first time we are landing on something which is not only unpredicted, but which is very rapidly evolving. And the way it's evolved has nothing to do with the way we thought it should evolve, because when you see a comet from long distances, you see global shing. Now we are so close to the surface that the way the outgassing proceeds is totally, unusually discovered. We didn't know it like that. One of the reasons why J is better than the others is because J is on the upper lobe, let's say like that, which seems to be less active. You've got to remember that if we chose November 11 to land, it's because at that point in time, the comet will be exactly at 3 AU, because we had to decide a criteria, and we said, well, we will land at 3 AU from the sun. What 3 AU from the sun? Because the information we had from the other comets in general, or the outgassing, is that below 3 AU, it starts to sublimate rather rapidly. So we wanted to have something as quiet as possible. So that's why we decided 3 AU. But now that we are there at more than 3 AU, it happened that this comet, at least locally, is already sublimating rather fast. We hope that from now to 2 months ahead of us, sublimation will not start much more than that. So all the work which is done, in particular flight dynamics, of course, is based on the fact that this comet will behave essentially as it is now. Most of the risk, as I see it, is that, of course, things go faster than we expected. No one knows what the comet will be in 2 months ahead of us. So the fact that we still have rather large uncertainties, to me, is based on the fact that we cannot exclude the fact that the drag forces, which are sort of equal to the gravity forces, may be higher than expected when we get there. So that's why 2 months is not large. 2 months might be a big difference between the activity level now and 2 months ahead of us. So it's normal that the people here take still big margin. We hope that by the end of the day, of course, we will know that the trajectory that they have worked on is still the one when we get there. But it's very, very rapidly evolving. And J, the quality of J in a sense that we are not very far from active region, we think, but the upper lobe, the smaller one, looks less active in a sense. So it might be that it will be more steady in time, and we are more confident that in 2 months ahead of us, it might be much closer to what we know now, that on the lower lobe in which you might rapidly expand the activity to rather far from the neck.
Thank you, Jean-Pierre. There's a question also from Twitter. Sungrazer Comets would like to know, do you hope to resolve the apparent contact binary nature of 67P? And, well, they even translated probably for me the question. That means, is it at all the same comet, or has it 2 parts?
It has 2 parts. The question whether or not these 2 parts are different that went together and collide at a given point and stick, or whether it's a single block that is going to explode into 2 parts in a while, frankly, the answer is not no now. It's debated. If you ask me my own position, I would prefer the second than the first alternative. But it's really something that people will work on when we have more and more data. You've got to realize that we have this data only for a few weeks from now. And the process by which we see the outgassing now goes in the direction, in any case, to amplify the disruption of this body into 2 bodies. Because, again, outgassing essentially is a matter of topography. As soon as you have a place where you start to sublimate, you increase the topography there. So obviously in the image that showed Olga a while ago, it was obvious that it's much more round in a sense in one place, not in the other. So we are starting to sort of disrupt the body into from 1 to 2 pieces. But again, that's my evaluation now. It's much too premature, I think, to make final decision there.
Just adding one short note to this, it might not, I mean, it's certainly not born in the shape we see it today. This is the residual, this is what we look at today. It might even be a fragment of a far larger comet. So this comet is not a typical size comet. So it might be just a fragment that then evolved to the shape we see it today.
And as a quick reminder, of course, this is also why it's important that we have 13 more months to go after the landing of orbiter science. And that time we will use to further investigate all of these things.
Thank you very much. Other questions from the audience? Yes, please. Then we need to wait a little bit.
Thank you. Sorry, Jean-Pierre Martin again. A question to Holger. Why is there so few images from Osiris published? It's not even one a day. Is there a kind of embargo or what? Sorry for the question.
No, I appreciate the question. So the short answer is we are not navigating the spacecraft. So the spacecraft, so the navigators, they need images every day because they are flying the mission. We have other needs. So we run sequences and we are looking for changes. So we want to characterize the surface, and we don't do this every day. So we run sequences from time to time, so from week to week, or even with 2 weeks cadence. And we dedicate some of the sequences to the surface, other to the global coma or the gas coma. So we aim for releasing an image every week, but we are also overwhelmed by activities. I mean, this is a warp speed program. We're getting more data down that even I can look at. We'll have to get through with it. So first landing, and then also, I mean, we are sciencing in the sense that we don't understand what we are looking at in certain areas, so we have to get an understanding on a team level before we can tell the story on what we see. So that's the short answer. The bit longer answer I will not tell, but the part of the story is also we have limited lifetime items. While the NAVCAM can take images as many as they want and need, we have a counted number of images coming down. So the more images we take now to share, the less images we have in the course of the mission. And we don't want to run out of consumables before we even reached perihelion.
Thank you very much, Holger. Well, okay. There's always a final and then there's another final. So maybe we take before the gentleman on the left side and then we take you again and then we see where we stand.
Stephen Young with Astronomy Now. I wonder if the panel would like to assess the complexity of this mission compared to other missions in space history. Just how difficult will it be to land on a comet?
It is, of course, it's difficult in absolute terms to say, well, this is the most complex mission ever, because there are things, little trolleys driving around other planets, which do magnificent things and are operationally very difficult. What is the element here for Rosetta is that there are many, many firsts that we achieve. We are flying alongside a comet. On top of that, we are then trying to land on a comet. We're doing many other things which are a first. And technically speaking, you will have understood from today that the shape of the body, the decision process we have to make because of the variability of the comet's activity, etc., complicates matters greatly, not only in space, but also on ground. As Holger already alluded to, the processing we just have to do for the landing site selection process is immense and it overwhelms everybody. And the same people in these teams also have to do the planning. So I would say the complexity in terms of operations, density and activities in space and combined with risks and mitigating risk, this is absolutely a unique mission at the top of the bill.
Maybe adding a few words on the landing itself, because this is indeed one of the particular challenges we have in this mission, that when we have designed the lander 15, 20 years ago, we had no idea on the target body. We had no idea on the size, no idea on the gravity, of course no idea on the shape or the surface properties. Actually, we were even designing it for a different comet, as you may remember. So this is completely different as compared to, for instance, missions that land on the Moon or Mars, where you have all these data, so you know what you are dealing about. And it's also connected to the event today, the landing site selection, because all of this information we have now was only or is only available since a few weeks or a few months. So in a very, very compressed mode, we had to select the landing site, and unfortunately we were lucky that when we designed the mission that we were accounting for a wide range of possible parameters, but when it was designed we had no idea. And for instance, one very important parameter is the surface strength. It is still not known. I mean, the comet looks more dusty, so this is an indication for rather soft material, but we do not really know. And when we designed the lander, our major fear was rebouncing on solid ice. This was one of our major concerns because of our ignorance how a cometary surface may look like.
Let me add to this that I feel this is really a historic moment in science. It's unprecedented, and I mean the meaning of this word is really it's a quantum step in cometary science. So we will get to centimeter resolution, and this will enable us getting closer to the clues of origin and what were the building blocks 4.5 billion years ago. So it's really a quantum step. It's a historic mission in that sense already now.
Yes, for Stefan Ulemek, what's about the gravity of the comet? We already discussed about it in Darmstadt, that you are feeling the gravity of the comet, and how this is going to interfere or cooperate with the landing process. Thank you.
Okay. Okay, the gravity on the comet is very, very low. It's a bit more than 100,000 on Earth. Yeah? So the lander, which is 100 kilogram, weighs on the comet about a gram. It's very low. But obviously it is significant because our scenario, our landing scenario, is based on the lander falling. So with this very low gravity, after being pushed away from the main spacecraft, it ballistically, the lander descends, falling down to the surface. So it is gravity. And after being released in some 20 kilometers altitude or so, it will at the end touch down with a velocity in the range of 1 meter per second. So that's walking speed. That's also an indication of how low gravity is. But yes, we need it. And we will also sit by gravity on the surface. We have to make sure that we are somehow anchored. That's why we have anchoring harpoons. That's why there is these screw devices in the feet you have seen in some of the images, because due to this low gravity, any kind of mechanical activity, in particular the drilling, would not be possible.
Okay. No hands going up. There's one question that I thought you would ask, but the good thing is it's a question I can even answer, which is, normally the experts are giving the answers. You did not ask whether J would be named J when we land. So we will do a public competition to name the landing site. And with this, I would like to thank foremost our panelists. So there's Andrea, Jean-Pierre, Holger, Stefan, and Fred for being here, but even more important for making this unbelievable mission come together from a management point of view, from the scientific point of view, from the engineering point of view, from the operations point of view. Thank you very much for this, and of course, good luck for the next 2 months. And thank you for being with us today. Ladies and gentlemen, you want probably to conduct individual interviews. This is possible now. I would like to ask you to please talk to Paul, talk to Roberto, talk to Brigitte, and they will make possible that you can interview those experts. Thank you very much, and this concludes the press conference today at ESA's headquarters. Thank you.